Good morning, students. Welcome to our online class for 5th semester AC Motors. On continuation of synchronous motors, we have learned synchronous motor construction, working principle, and different salient points. In this class, we are going to learn how the synchronous motor can be used in industrial applications as a synchronous condenser. Similarly, what are the applications of synchronous motor in our power engineering? You can see this figure is a synchronous condenser used in a big industries to improve the power factor. Let us see one by one in details. The topics regarding to 5th semester EE 503. Last class we have seen that synchronous motors starting methods. As we know that synchronous motor is not self-starting motor. That purpose we use different type of the methods by using mechanical prime mover and damper windings. Now, today objective is on completion of the topic you should be able to understand synchronous motor used for power factor improvement alone, dual purpose synchronous motor, that is load as well as power factor improvement, problems on synchronous condensers, simple problems, mathematical proofs, and applications of synchronous motor in our power engineering field. Now, synchronous condenser. Condenser we already known in first year level. It is a capacitor. The capacitor is a two plates, conducting plates separated by dielectric media between the two plates. It is capable to store the charge particles, electrostatic field. Generally, this capacitor can be used to improve the power factor in our electrical fields. It maintains a constant voltage. It avoids change in voltage in the line where it is connected. Same principle can be used here. We are going to convert our synchronous motor as a capacitor, as a condenser. How? This is a motor, but how we are going to convert our synchronous motor into capacitor or condenser? Is it possible? If possible, how it can be used to improve the power factor in our industries? Let us do problems also, proof purpose. Okay. Now, what do you mean the definition? Synchronous motors, as you know that we can operate at different power factor levels with the help of DC excitation to rotors. The DC excitation changes the back EMF produced in the stator. Three conditions, as we know that when the induced back EMF equal to the terminal voltage applied at stator, first condition, normal excitation. Under excitation conditions, whatever the back EMF induced in the stator is less than the terminal voltage. And final condition, when overexcited the synchronous motor, the back EMF induced in the stator is greater than the applied voltage. As already we have seen the vector diagrams, how the load angle alpha, the internal angle theta, and power factor angle phi changes based on excitation in previous classes. At the same time, we also performed a few problems on this. Now in this case, so we are going to operate our synchronous motor over excitation condition, that is equal to overexcited normal DC, whatever the 110 volts we are going to give. At that condition, we are going to extra DC supply is given to the rotor through the slip rings. The overexcited synchronous motor operating on no load condition is called as a synchronous condenser. There is no load on the motor. We are excited the rotor with overexcitation. This situation we can say it synchronous condenser of synchronous motor. So it used as a power factor improvement device or phase advancers. So a condenser or a capacitor always draws a leading current from the AC system. It is known that a synchronous motor can be operated at unity power factor, lagging power factor, leading power factor just by changing the excitation to the rotors. Rotor, only single rotor with slip rings. The ability of the synchronous to operate at leading power factor when overexcited is utilized in improving the power factor of the system. When a synchronous motor is used for power factor improvement alone with no mechanical load, it is called a synchronous condenser. We can say it meets a small losses, the constant losses, the friction and windage losses, some iron losses, some part of copper losses. So then we are overexcited the DC synchronous motor, then it operates as a synchronous condenser. This draws a leading current as does a static condenser which is connected in the line. Similar to the static condenser, it behaves as a condenser. If you are connected one capacitor to the line, it will draw the leading current. Same our synchronous motor, if overexcited with minimum load on the motor or no load on the motor, it draws the a leading power factor. That means it creates the reactive power generation. Hence the name synchronous condenser. This is useful for installation where the power factor is low. At no load, we are neglecting the losses. So first class we have seen that. So where the stator magnetic axis and rotor magnetic axis both are coincides. I think you remembered all things this one. The stator and this is stator magnetic field, the north pole and south pole. Then rotor magnetic field, here we usually know that rotor, south pole and north pole both are coincides. This is axis, same axis. Then what is the difference between the two? So, that is equal to alpha, we can say the alpha is equal 0. Both magnetically locked each other and it rotate at a synchronous speed, ns is equal to 120f by p. Under we are assumed as a neglecting all these constant losses. At this condition, whatever the EB generated, EB back EMF generated in the stator and whatever the voltage applied to the stator V, then almost are equal in magnitude but in opposite to each other. That means here we have the V and here it said we are taking the EB. Then both are magnitude is equal but out of phase, 180 degrees phase. At this condition, what happened already we have seen. This is a at no load, we are neglecting this situation. Now, synchronous motor operates at alpha load angle, internal angle, that is equal 0, coupling angle. Now, this means V and EB are out of phase. You can see here the variable capacitor, it acts as a variable capacitor. In this case, so overexcited field coils, then the whatever the back EMF induced in the stator is greater than the applied voltage. For example, if our motor is operating at, for example, 400 volts, due to the DC excitation to the rotor, DC supply, and here the stator winding try to generate the voltage. That voltage is greater than the 400 volts, that may be 500 volts. This voltage is always opposite the cause of its production, that is equal stator voltage. This is equal to V, this is equal to EB, that is the back EMF. Back is always back to the applied voltage. Then what is the difference here? EB is equal to 500 is greater than the 400. At this condition, so we know that the current is leaded by the supply voltage by angle of maximum 90 degrees. Now, the current drawn from the supply, this current is now leaded by 90 degrees. As we know that, so if motor is excited, overexcited, by changing the DC supply, we are going to change the current from lagging power factor to UPF to leading. Just simple changing this one. So, in this synchronous condenser, we are going to excite the DC supply to the rotor conductors, and at this condition, so it acts as a overexcited condition. In this condition, it is equal to back EMF induced EB is greater than the applied voltage. During this period, it draws the current from the supply in a leading power factor. That means it generates a large reactive power. Now, what happened you can see here. The armature current, that is equal to, as we know that armature current is equal to EB minus applied voltage minus, simply we know that. So, what is the formula? So, what are the motor here? So, applied voltage is equal to V voltage and a generated voltage is equal to EB. In between there is a that is equal to ER, the losses, that is the ER, resultant voltage. That is equal to, we can say that ER is equal to IA ZA synchronous impedance, or we can write it that is equal to V minus EB. In this case, EB is greater than, then we can say that EB minus V. So, I want the armature current, then armature current is equal to EB minus V by ZA. So, similarly, here ZA is equal, what is the synchronous impedance, that is equal to RA plus J of XA. RA is the resistance of the winding and XA is the reactance of the winding. So, later in this case we are taking, so XA is a very greater than the RA. So, we are neglecting this value. So, instead of total synchronous impedance, we have the synchronous reactance only. That is why we written the here XS. So, all this we studied in previous classes. Now what is happened? Due to this one current, IA is equal to EB minus V by XS, the current magnitude at an angle of leaded by the voltage, applied voltage is nearly 90 degrees. So, that means we can vary the armature current from unity power factor to the lagging power factor. We can see here from this can maximum 90 degrees we can vary current. We can change simply. These are the IAs, armature current. The angle, the power factor of phi is changing. So, this acts as a capacitor. For example, what will happen if the same DC supply is under excited, then what will happen? The current, which is voltage V, and due to the DC supply of rotor, then induced EMF is always less than the applied voltage. At that condition, so what is the same formula? You can apply it. IA Z A is equal to V minus EB. Then I want the IA. So, we are going to that V minus EB by IA. Sorry, XS or ZS. Now, in this condition, the current which is drawn from the supply is equal lagging power factor. That means the V is this direction, then I is this direction. Maximum is the 90 degrees. V and IA. So, you can see here V, this one lagged by the 90 degrees maximum under excitation condition. So, now in this case it will draw the more reactive power to the motors, hence the power factor is lagging condition. Okay, IA is equal to V minus EB by XS, where this is equal condition, and IA lags the applied voltage by 90 degrees. This gives the variable inductor operation. That means by changing the DC supply to our motor act as a condenser capacitor, as well as if possible we can use it as a inductor. As we know that the inductor always draws the reactive power and capacitor always creates the reactive power. If reactive power is more in our system, then automatic power factor increases. If reactive power consumed from the system, the system becomes the lagging power factor. Dear students, you can observe with the beauty of the synchronous motor. The synchronous motor, by simple excitation of the rotor, our motor acting as a capacitor, acting as an inductor. These basic principles are used in our system where we are going to change our power factor. As we know that under normal condition, so nearly 75% of the load in our power system is the induction motors, heating furnaces. So, this will try to draw the reactive power from the supply. Then total overall power factor is a lagging power factor. Then what will happen? In our substation, to improve this voltage, terminal voltage in the line, we are going to use the OLTC, online tap changer. By changing the tap, we are going to increase the terminal voltage. Then even then, by changing the maximum tappings in our power transformer, in our substation, we are unable to meet the end voltage to the normal value. At that condition, we are going to switch on the capacitor banks in our substations. By using the OLTC, we have generated the reactive powers. Even then, further we required the capacitor banks switched on. Then the terminal voltage is increased to the normal value when load on our power system is more and more. Then in this condition, suddenly load is collapsed, load is reduced drastically. Then what to do? So we are going to use our capacitor banks first of all switched off. Then even then the terminal voltage at the receiving end voltage is more due to this OLTC is a tap. Then we are going to reduce the OLTC tap. Then the voltage is coming to the normal value. For example, even then in this condition the receiving voltage is more than the sending voltage due to the capacitance of the long transmission lines. Now what to do? We are used OLTC, we switched off the capacitor banks. Then even then the receiving voltage is more than the sending voltage. How to compensate it? Otherwise there is a high voltage in the receiving end side. The consumers may be objectionable. At that condition, so we are going to add some inductive load on the system. So in our substations we also readily available reactors. So connecting the reactors, it consumes the whatever the excess reactive power in the system is consumed by these reactors. So the voltage automatically comes to the normal value. If you use this reactive power reactors in substations, then even then the receiving voltage not in up to level. The terminal receiving voltage is more than the sending voltage. Then what to do? If you are connected this synchronous motor at the end, receiving end, if this now the synchronous motor is operated under excited condition, then instead of previously it generated the reactive power, now it is consume the reactive power, then it acts as inductors. And under excited condition, same our synchronous motor now draws the current from the supply is a lagging power factor. Then whatever the terminal voltage drastically changes to the normal value. Dear students, you can observe it. Simple by changing our capacitor bank. It is a sharp knife, we can use a multi-purpose. Similarly, our synchronous motor, if used, we can operate to generate the reactive energy, or if not possible, I require consume the reactive power by changing capacitor condenser to inductor, purely the same characteristics. That is the beauty of this synchronous motor. That's why this is a very costly. Okay. Now we can. This is not simple. It's simple explanation. There is everything is a mathematical proofs, because we are the engineers. We have to assume this some values. Based on this one, we are going to do the mathematical calculations. We can do that one also. Okay. So now you can see here. Suppose what is this one? The induction motor. The induction motor always, the inductors always draw the lagging power factor. Let us assume this motor is drawing the current. This is a rating of the some, for example, so 10 HP induction motors. It is drawing the active power in the kilowatts from the supply. In the operant power is a kVA, some supply, and reactive power also drawing from this one kVR. So what is the kilowatts, what is the kVA, what is the kVR? Active power, reactive power, operant power draws from the supply. Due to this condition, what will happen? So always the lagging power factor, the current always lagged by the voltage by some angle, that is the power factor angle, cosine angle. The induction motor takes lagging kVR from the supply system to set up a air gap flux. So as we seen, whenever the three-phase supply is given to the stator, it establishes a rotating magnetic field in the air gap. To produce this rotating magnetic field, we require some energy. That energy is taken from the supply, but it is in a lagging power factor. Hence, it operates at lagging power factor. This results in poor operation of a overall system power factor. At the same time, it will draw some more current from the supply. The motor cannot be operate 100% its rating. Now, in the second case, what will happen? A overexcited synchronous motor is connected in parallel with the induction motor. So, a big motor is connected in our industry in addition to the all induction motors which are drawing a lagging power factor. Now, in this case we can see, just like students, you observe it in our house, there is a UPS in your home. Now, what will happen if the power comes from the DISCOM, NPDCL, CPDCL. So, directly whatever the power comes, that is stored in our batteries through our UPS system, and at the same time it will gives to our normal usage loads. Then whatever the units consumed energy from supply. Now, what will happen if there is no supply from the DISCOM people? So, whatever the stored energy in our house from battery is given to our loads through the inverter. Here, just like it is emergency purpose, whatever the energy stored in the form of the DC is converted to the AC through the inverter, that is given to the emergency loads in our domestic houses. That is, here the power is supplied to the local. Whatever the emergency loads is required, for example, one light, one fan, emergency purpose in the night we require energy from these local arrangements. If power comes, no need of this one. Similarly, here whatever the power that is here we are taking the kVAr, reactive power. So, normal the induction motor which will always draws a kVAr, reactive power, from the supply in lagging power factor. Due to this one, what will happen? It will draw the more current in the line. At the same time, the performance of the motor may not be that rating, some percentage reduced due to the drawing the reactive power from the system. If you are connected in parallel to our synchronous motor, if it is operated with no load, with over excitation, and it will generate the reactive power that is supplied to the local motors. So, due to this one, what will happen? The burden on the transmission lines is reduces. So, locally it will supply to the induction motors, then overall system increases. You can see, so due to this one, from whatever the kVAr reduced kVA also on the industry, and same kilowatts and kVAr supplied to our induction motors from our local synchronous motor. Okay. So, we can see that means here what is happening. So, under normal condition, if there is no connection here, so whatever the current taken from this one, the kVAr is the reactive power taken from the supply is increases. Then what will happen? That is supplied from the lines. So, lines subjected to the burden, overcurrent in the line, lagging power factor. So, the lines may be heat takes place, ice current or more current will flow through the lines, losses may be takes place. Instead of that one, we can avoid it. How we are going to add it? So, whatever the reactive power generated from this one, so that is supplied from this one only. No, this extra needed, that is the power is taken from this one, no current is flowing this one, then what is happen? No transmission losses takes place. That is helpful of this synchronous motor. Now, what are the salient points? You can see A overexcited synchronous motor is connected in parallel with the induction motor. It supplies a lagging kVr locally as shown in the figure. Distribution lines are relieved of completely supplying the lagging kVr needed by the induction motor. Now, what is the need? We are prepared in house itself. So, whatever the biryani we required, generally we taken from the outside due to the corona. Now, in house itself we are prepared the biryani. Then what is the need of the taking parcel from the outside? The safe side we are prepared in home only. That is a healthy. Similarly, so it relieved the transmission lines due to the overburden. The supply lines have to handle a reduced kVA and a reduced current. This leads to better operation of the overall system, better voltage regulation and lower line losses, and efficiency of the system increased in the distribution lines. The induction motor still operates at the same lagging power factor because inductor always draw the lagging power factor only. So, observing the same kVr and kilowatts. It is the combined load consisting of overexcited synchronous motor and induction motor will work at improved power factor. If the lagging kVr demand required by the induction motor is completely met by the over-excited synchronous motor locally, the combined load operate at unity power factor, because our induction motor is a lagging power factor, our synchronous motor is a leading power factor. The combined, it becomes the unity power factor. It should not be lagging power factor, it should not be leading power factor. I require the UPF, unity power factor, that can be met by using controlling the DC excitation to the rotor of synchronous motor. The power factor is improved from some angle to angle. Now, so these are the some theoretical part. So we can see the in mathematically in the next class. So here you can see it. So for example, a mathematical value here in the kilowatts taken is the active power, and reactive power taken, this reactive power taken is this one. Then this whole square plus this whole square, we are going to the kVA apparent power, active power, reactive power, apparent power. As we know that this is the angle, power factor angle. So this is a reactive power which is taken from the supply. Actually no need to supply this one, but always induction motor will draws. If this reactive power is increased further more, then what will happen? This angle increases. The angle increases, further lagging power factor. Instead of this one, this direction, instead of this one, suppose it is this one, what will happen? The angle reduces, then power factor improves. That means always this voltage, this angle, this value should be, this both should be in phase. Then so we are going to the UPF. Okay, so that means this should not be this maximum 90 degrees, maximum 90 degrees. The leading is a lagging. So actually we are going to try to maintain this kVA in the same direction. That's a UPF. Okay, so we know the power triangle. What is the formula? So L formula, power triangle is kVA whole square, kilowatt whole square plus kVR whole square. The power triangle formula, you know that. I want the kVA under root of this one, we are going to get it. Okay, simple if you are connected the only induction motor. If you are connected the both motors, what happen? So here same formula we are going to use it, kilowatt, the J constant of this value. Now, as you know that if both are connected, in our synchronous motor performance values, you can see the vector diagram also. How here the voltage EB changes and V changes, then current you can see the IA is coming from the leading power. So, this is the voltage, you can see this is the voltage and the current is this direction IA. So, what will happen? So, power factor lead it. You are over excited, no load on this one. Then this is a small angle of alpha to meet the constant losses. At this condition here, so whatever the EB is the greater than and V. Then the current which is drawn from the supply is the leading power factor. This is a vector diagram. Now let us see how this one happened. So this is a, for example, on this one you can see only under normal condition the kilowatts. So what is the active power? kW1. Let us assume this one. Now in this case, first is the active power is a kilowatt 1 and kVA is a kVA 1, this is a, and this is a reactive power. Active power, reactive power of this value. What is the value? kVR 1, kVA 1 and kilowatts. So kVA 1 is equal to kW1 whole square plus kVR 1 whole square. This is the if operated only single motor. If now this synchronous motor is operated under overexcitation condition. At this condition, what is happened? You can see the diagram, how it changes. Now you can see it. Next case, we added the synchronous motor. Its active power is equal to kW2 and its kVA is equal to kVA2 and its reactive power is equal to, this is equal to kVR2. You can observe this is this direction, this is this direction. Okay, kVR2 leading, kVR2 lagging. Now this is this value generated, this is this value generated. Now this value is higher, this value. This is a lagging value, this is a leading value. For example, this is equal to 10 kVR1, kVAR. This is equal, for example, 4 kVAR1. This is generated the reactive power, it is consumed the reactive power. Then overall what will happen? So total is equal 10 minus 4 is equal to 6 kVAR at the system. That means whatever the year 10 minus this 4 value, then remaining value is going to, instead of this value, it is going to this value. That means here it changes. You can see it. Now this, if connected the synchronous motor, if we connected the induction motor, we are going to get the two power triangles. One is the kVA 1 and kVA 2. Now by combining these two, one is the generating, one is the consuming, then we are going to get that. So resultant total kilowatts is the active power is equal kW1 and total kVA is equal this one and this is total kVAR is equal this one. That means, so whatever the value, so this value equal to this value and subtracting total value, we are going to this value only, that is this value. So overall system now kVRT total kVR only takes from the supply is equal this much reduced. In previous case, this of the amount of the energy taken by this one. Now from this value to only this value we reduced by connecting the synchronous motor. Okay, so this is a basic idea how this is reactive power changes in the system. Dear students, we will see remaining part in the next class, the continuation of this one and applications and few more practical problems we will do. Okay, so here these are the points. So same things, the vector diagram. Okay, so in kilowatt W, total kilowatt is equal kW1 plus kW2, and that means here the total this power is equal to, total is equal to up to this plus this one, both are kW1 kW2 active powers. At the same time reactive powers, this is equal to what is the value, this value plus this value, this value plus this value. Okay, next, and so we are going to get the total kVA kVA is equal kVA1 plus kVA2. All are the vector sum. The total kVA2 is equal kW plus active power plus reactive power, as you know the power triangle. Then what is the power factor? Now here we are going to get that. So finally we are going to get, this is the final value. This is the angle. So I want the cos phi. Cos phi is equal, what power factor? Cos phi is equal to, so this value, what is the value? This is the kW T total divided by, this is the total kVA, that is cos phi. So we are going to this one. Now what is happening? Here the power factor is improved, angle is reduced, then power factor improved. If it phi is equal 0, we are going to the UPF. Okay. So that means we can change it from this value to this value, where the angle, whatever the angle is this much, is reduced to the very low value, then power factor improved to this value. This is a vector diagram, this is a phasor diagram. From this one you are going to understand how this happened with the system. Okay. So we will see this continued problem, practical problem next class. Okay. So this the time is up. Thank you.